So this video, I want to talk about the order of reaction, straight to the order of reaction, zeroth order, first order, and second order. But before I go into that, let me just brief reaction kinetics. I've done two videos on reaction kinetics in my channel. You can check it out. But let me just say brief things about reaction kinetics. Let's talk about the factors affecting reaction kinetics. We have light, nature of reactants, surface area, how they contact themselves, and stuff like that. You should know that one, factors affecting reaction. If you don't know it, there's a video in my link in my channel. You can watch it. You should also know the molecularity of a reaction. If you have A plus B giving C, if you ask for the molecularity, it's just the number of mole of the reactant, like the number of mole of the total reactant. Here is one. Here is one. That's molecularity is 2. That's bimolecular. Let's say this one is 2A plus 1B. 2A plus B. That's 2 plus 1. That'll be 3. That's thermolecular. And just like that, sure. You should also know order of reaction. Like when they talk about the overall order. Let's say we have A plus B, A plus 3B giving C. And you should know that to find the order of reaction, you cannot find the order of a reaction from the equation of a reaction. You have to do experiments. But when they say in an elementary reaction, or in a hypothetical reaction now, or elementary reaction, you can get it from the equation. But originally, you cannot get order of reaction from the equation. You need to they need to do the experiment before they can get it. So in the question, they always write something like in the elementary reaction. In the elementary reaction, the equation is this: find the overall order, or in a hypothetical reaction, something like that. They will not just say what is the order of this reaction. They need to write that in an elementary reaction, in a hypothetical reaction. So here now, let's say this is a hypothetical reaction, elementary reaction. The overall order is, since here is 1, that's 1 plus 3, that's 4, that's fourth order. So that's all about order of reaction. And you need to know Rate's law. You need to know Rate's law. Oh, wait, let me say something about order of reaction. When it's in the first order, let's say this is Rate's law. This is your Rate's law here. A raised to power n. This raised to power n is your order of reaction. This A is your concentration, but in the bracket. This K is unit of rate constant, and you should know that this unit of rate constant, the only thing that affects it is temperature, and this R is rate of reaction. So when you have this now, when you double a reaction, and when you double the concentration of a reaction, and the reaction also doubles, it shows that it's a first order reaction. How do we know? This is the rate of reaction here, and first order is raised to power 1, because this n will be 1. First order is raised to power 1. So that's R is equal to K. When we double this reaction, it will be 2A, Abi. It will be 2A. But it's the first order reaction is 1. So when we double this 2A raised to power 1 is still 2. So it's still 2A. The reaction will still be 2A. But let's say it's a second order reaction now. Let's say the second order reaction. That's this n will be 2. Because the second order reaction now raised to power 2. So let's say we double the equation in the second order reaction. That will be 2A, Abi. Since we doubled it, 2A. But it's the second order reaction, it's raised to power 2. So that will be R is equal to K. 2 raised to power 2 is 2 times 2, that's 4. That's 4A. 4A. So you can see that when in a second order reaction, when we double the concentration, the rate was quadrupled. When we double the concentration, the rate was quadrupled. You can see it's 4. That's quadrupled. So if it's third order reaction, that will be 2 raised to power 3. That will be 8. If it is fourth order, 2 raised to power, and that's how we're going to be doing it if you double it. But you can also triple it. If you triple the concentration, that will be 3 raised to power 2. Stuff like that. Just know the Rate's law. If you can know this or Rate's law, then I'm going to do. Still know that too. So that's all about the basics. Yeah, so now let's talk about order of reaction. So we have different kind of order reaction. We have zeroth order, we have first, second, third. It can also be in negative and it can be in fractional. But here we are going to talk about zeroth order, first order, and second order. So I'm just going to give you the summary of everything that you need to know about zero, first, and third. So the first one is the rate of reaction. In zero order, the rate of reaction is from Rate's law. You know Rate's law is R is equal to, these are Rate's law. R is equal to K, then the concentration raised to power the order. So that's our, so we are going to be making use of this one. So here, our zeroth order is going to be K is equal to A. K times A, but this our order of reaction is 0. And anything raised to power 0 is 1. So that's R is equal to K. R is equal to K, A raised to power 0. Which is still R is equal to K because anything raised to power 0 is 1. That has to show you that in the zeroth order reaction, the rate of reaction does not depend on concentration. Why, if it's first order, this one is just going to change to 1. This one is going to change to 1. So our first order, the rate of reaction will be R is equal to K A. Whereas n to the power 1 is still as stuff, so we don't need to write the 1. Why for second order, this stuff will just change to 2. So for second order, it's going to be R is equal to K A raised to power 2. So that's the rate of reaction. The rate for zeroth, first, and second. Now let's talk about the specific rate constant. This K is called rate constant. This is our K is called rate constant. And that's the formula. The formula for determining the rate constant is m raised to power 1 minus n t raised to power minus 1. Where this m is concentration in molar or mole per dm cube, while t is time in seconds. So let's say we want to find the rate constant, the specific rate constant or rate constant for zeroth order. Since it's zeroth order, it will be anywhere we see n, we just put the 0. So that's m raised to power 1 minus 0 t raised to power minus 1. That's m raised to power 1, we see m t raised to power minus 1. So that's our m t raised to power minus 1. That's the specific rate constant for zeroth order. If it's for first order, now let's do for first order. That will be m raised to power 1 minus 1 t raised to power minus 1. 1 minus 1 because it's first order, so we have to substitute 1 where there's n. So 1 minus 1 is 0. That's m raised to power 0 t raised to power minus 1. And n t raised to power 0 is 1. That's our final answer is 2 t raised to power minus 1. So the specific rate constant for first order reaction is the unit. We call it unit of specific rate constant. Unit is t raised to power minus 1. So if this t raised to power minus 1 is t time in seconds. So anytime you solve a question first order and you're getting the specific rate constant, you're getting the value, the unit will be in per second. It can be in per second, per day, per hour, but it's only going to have time per time. You can see it can be per second, per day, per hour, depending on how they want you to give your answer. So let's do for second order. Specific rate constant is equal to m raised to power 1 minus n t raised to power minus 1. So for second order, it will be 1 minus 2 t minus 1. That will be m raised to power minus 1 because 1 minus 2 is minus 1 t raised to power minus 1. So our specific rate constant for second order will be m raised to power minus 1 t raised to power minus 1. And don't forget that your m is mole per dm cube. Your m is mole per dm cube. If I also want to trick you with this thing, your m is mole per dm cube. So let's say for second, as you have m raised to power minus 1, this will be r raised to power minus 1. So that will be mole per like mol raised to power minus 1, mole raised to power minus 1, dm cube. These are your answer will be. Then you now write time, maybe per second. For your second order, because they used to give this kind of question. They say you find the unit of the rate constant for the second order, then they'll give you mole per dm cube per second. You should know that it's mole raised to power minus 1, dm raised to power 3, then per second. So that's that on the unit of rate constant for 0, first and second. Now let's find half-life. For half-life of 0th order, half-life of first order, and half-life of second order. For 0th order, the half-life is concentration A over 2k. A over 2k. That's the half-life for the 0th order. While for first order, it is ln 2 over k. Ln 2 over k. You should be familiar with this before in radioactivity. So that's to show that radioactivity is a first order reaction, because the half-life is ln 2 over k. Ln 2 over k. While for the second order, the half-life is 1 over ck. These A and C, they just mean concentration. That's the meaning. It means concentration. That's all. So this is to show you that the half-life of a first order reaction does not depend on concentration. Because when you check the formula, you cannot see any concentration there. This is rate constant. This is ln 2 at 0.693. You cannot find concentration here. So the half-life of a first order reaction does not depend on concentration. Why here for 0th order, the half-life is inversely proportional to the rate constant. So let's just say the half-life is directly proportional to the concentration. So as half-life is increasing, concentration is also increasing. While for second order, the half-life is inversely proportional to concentration. So as concentration is decreasing, half-life is increasing, and as half-life is decreasing or increasing, this one is doing the opposite because they are inversely proportional. So that's that about the half-life of the three of them. Now let's talk about their integrated law form, their integrated rate law. So let me explain this thing. So the integrated rate law for our 0th order is just A final minus A initial is equal to minus kt. A final minus A initial is equal to minus kt. You should notice A final minus A initial is equal to minus kt. Or you can write it like this. Let's say if A final minus A initial is equal to minus kt. Or you can write it like A final is equal to minus kt plus A initial. This A final initial is final causation initial concentration. For our first order reaction, it is ln b over b minus x is equal to kt. Ln b over b minus x is equal to kt, where this b is the concentration, the complete concentration, mostly 100% is complete concentration, while this b minus x is concentration after the reaction. While this one is initial concentration, this one is final concentration after the reaction, initial concentration. While for our second order, 1 over c minus x minus 1 over c is equal to kt. So this is the integrated rate law for 0th order, first order, and second order. So you need to know this formula because there are going to be certain questions from it. This t is time, this k is rate constant, this one is initial concentration, this one is final concentration. A here too is also concentration. C here is initial concentration. C minus X. C minus X, everything like this is final concentration. B minus X also, everything like this is final concentration. So you need to know that one. Now, questions also used to come out from all these graphs. Graph of first order, graph of second order. They'll tell you what are you going to plot against what to give a straight line. So I'm going to explain that one. So in first order reaction, let's find out how they got the graph. So the integrated rate law is like this. For first order, ln b over b minus x is equal to kt. And we want to represent this ln, we want to change it to log. And don't forget that I've said it in one of my videos in thermochemistry that when you have ln x is 2.303 log x. You should know this, and this is how to convert ln and log. Ln x is equal to 2.303 log x. So we are going to be using that. So let's say we have ln b over b minus x, that will be 2.303 log b over b minus x is equal to kt. So we'll just divide both sides by 2.303. That will be log b over b minus x, log b over b minus x is equal to kt over 2.303. kt over 2.303. Can you see it? Log b over b minus x is equal to kt over 3.303. So now we want to find what we are going to plot against what to give us a straight line graph. So this is the graph here. This is the graph. Now we are going to compare this to a straight line graph. So y is equal to mx plus c. Mx plus c. We want to make this information here. We want it to resemble a straight line graph. And the equation of a straight line graph is y is equal to mx plus c. In fact, let me clean this graph. Let me do the graph here. So we want it to resemble this stuff here. We want it to resemble y is equal to mx plus c. So we know log b over log b minus x can be written as log b minus log b minus x is equal to kt over 2.303. Law of logarithm, log b over b minus x can be written as log b minus x. So what's next? We'll bring this log b, we'll take it to the other side. We'll take it to the other side. That will be minus log b minus x is equal to kt over 2.302. Kt over 2.303 minus log b. So let's clean this. You don't need it. So kt is equal to. Now we don't want this negative here, so we'll multiply all through by negative. So when we multiply all through by negative, we'll have log b minus x is equal to minus kt over 2.303 plus log b. You can see we multiply all through by negative. Negative and negative is positive, so log b minus x minus kt over 2.03 plus log b. Now let's compare this into equation of a straight line. Equation of a straight line is y is equal to mx plus c. So you can see here that y is log b minus x. You can see y is equal to log b minus x. The slope will now be m is equal to minus k over 2.303. This t is x. This t is our x component. Y slope is minus k over 2.303. Why our intercept is now log b. Now let's draw the straight line with that information. So let me clean this. So this is the graph. This is our y-axis, this is our x-axis. So our y-axis here is log b minus x. So on the y-axis, instead of writing y, we write log b minus x, log b minus x. Y on the x side is time. So this is to show you that to get a straight line for first order, to get a straight line graph, we are going to be plotting log b minus x against t. So all these stories that I've been saying, all you need to know is, if they ask you the question, what are we plotting against what? We are going to be plotting log b minus x against t to get a straight line. But that straight line, the slope is minus k over 2.303. That's minus, the slope is negative. So the slope is not, the straight line is not going to be going up. Instead, it will be coming down. Why? Because the slope is negative. So we are not going to be having something like this. Instead, we are having something like this. It is going down. We are going to be having something like this because of this negative slope. So your take home, to get a straight line for first order reactions, to get a straight line graph, we are going to be plotting log b minus x against t. Let's do same thing for second order reaction. What do you plot against what to get a straight line graph? You know, in the integrated law for second order, we have 1 over c minus x minus 1 over c is equal to kt. So you want to modify this in a way that it resembles the equation of a straight line. So you can just say 1 over c minus x, so this one is the final, is equal to kt plus 1 over c. We brought 1 over c from the left, we took it to the right. That's why it became plus. So that's plus 1 over c. So we just represent this with a straight line graph. Y is equal to mx plus c. Straight line equation, y is equal to mx plus c. So you can see that our y-axis is 1 over c minus x. Our slope is positive k. That's k, positive k. Our x is time, and c, our intercept, is 1 over c. So to draw the graph like this now, let me draw the graph. Let me clean this please. Now to draw the graph, this is the graph. To draw the graph now, y is 1 over c minus x. So our y-axis will be 1 over c minus x. Y is equal to 1 over c minus x. Our x-axis will be time. That's time in the x-axis. So we are going to get a straight line graph when we plot 1 over c minus x against time. This 1 over c minus x, they can say it in a verbal form, like plotting. So just plotting the inverse of the final concentration against time. So we are going to get a straight line graph. But this our straight line graph will not start from the origin. It will start from here. And it's going to go in the positive direction because our slope is positive. But it's not going to start from origin, it's going to start from here. So this is the graph for second order. And to get the straight line graph, we are plotting 1 over c minus x against time. So lastly, let's talk about Arrhenius equation. What Arrhenius equation is just trying to show is how temperature and rate constant are related, because I said earlier that the only thing that affects rate constant K, the only thing that affects specific rate constant K is temperature and nothing else. Only temperature affects K. So we are looking for the equation that connects K and temperature. And that equation is K is equal to A exponential minus EA over RT. So this is the equation where K is specific rate constant, A is pre-exponential factor. E here is our activation energy. This one is molar gas constant, and T is temperature in Kelvin, our absolute temperature. So when they give you degree Celsius, you convert to Kelvin by adding 273, of course. So here is our respiration factor, and this is our specific rate constant. So this is the formula to use when they say give you a question on Arrhenius equation.